7. So that's less than 7. Okay. So this implies that bringing the two operands within the absolute value gives us that x minus 3 times x plus 3. That's the absolute value of them. Must be less than, well, it must be less than 1 times whatever x plus 3 is bounded above by. So it must be less than 7. Okay? Which implies when we multiply this out that gives us x squared minus 9 must be less than 7. But we know from the choice of delta being the minimum between 1 and epsilon over 7, we know that 7 is less than epsilon. So that's actually less than epsilon. So what we actually have here is we have just shown that x squared minus 9 is actually less than epsilon when we chose delta to be equal to 1 to be the minimum of the two possibilities, which is exactly what we wanted to show. This, I suppose, is case. This here now is case 1 when delta is chosen to be equal to 1. Let's have a look at case 2 when delta is chosen to be epsilon over 7. So let's say for argument's sake, let me put the top on this. Let's say that epsilon over 7 is the min of 1 and epsilon over 7. So let's choose delta to be equal to epsilon over 7. And let's start the argument again. So start with the premise. So we have this from the premise we have, excuse me, let's just say here, from the fact now and the premise, that we have x minus 3 is less than delta, and we're choosing delta to be epsilon over 7. Well, this implies that x minus 3 times x plus 3, don't forget, we know what x plus 3 is bounded above by. X plus 3 is bounded above by 7, okay? So we now know that x minus 3 times x plus 3 must be less than epsilon over 7 multiplied by 7. X minus 3 is actually less than 7. X minus 3 is less than epsilon over 7. So the product of these two must be less than the product of them two. So what does this imply? This implies, once again, bringing the operands within the overall absolute. This becomes x minus 3. Absolute value of x minus 3 times x plus 3 is what we had before. Must be less than, well, epsilon over 7 times 7 gives us epsilon, which implies that x squared minus 9 is less than epsilon. And once again, what we have here is this is f of x minus L is less than epsilon. Okay, so from the fact that we had this is x minus a is less than delta, what we derived f of x minus L is less than epsilon, which is what we had to do. And this is, I suppose, this here is case 2 when delta equals epsilon over 7. And in relation to case 1, once again, we started off with the fact that x minus a is less than delta, and we ended up with the fact that, once again, here is f of x minus L is less than epsilon. So once again, we've proved it for both cases, which is effectively what we had to do. Is once we found the delta, we need to prove or we need to infer from this particular premise, we need to infer this conclusion, which is exactly what we've done in both cases. Okay, guys, once again, this was Jonathan Lambert with Maths and Stats, and I hope this video, another video in a series of videos dealing with calculus and limits, and in particular Epsilon-Delta proofs, but primarily focusing on probably one of the simplest quadratic equations that we have. What we've actually shown here is how to prove that using an Epsilon-Delta argument. So once again, thanks for watching. I hope that this video was intuitive, and more importantly, I hope that was helpful for you. And thank you. Bye-bye.